Hello students, welcome to We Learning and I'm Lavanya Lungovan, your science educator. So how are you all? Are you all safe? Fine? Good? Very good. So before we just start with the session, tell me, am I clear? Is my voice clear? Is my video clear? Give me one thumbs up so that we'll just start with the session. Good. So We Learning, you know very well, right? We Learning is an online education platform. Here we give quality education for all students. Here at Vistas Learning, we help students to stay on schedule, value their time, and also excel in their academics. So, you have to just subscribe to our channel and stay connected. And also, share this with your friends, family members, and relatives because someone out there will have the access to quality education. Correct? So having said that, let's start today's session without any further delay. So what are we going to discuss today? Good. It is all about atoms. So now tell me what is an atom? If I just come and tell you atom, what comes to your mind? Or just recall and tell me from which grade are you hearing this particular term atom? Yes, maybe from your 6th or 7th grade? Correct. Yeah, from your 7th grade onwards, you will learn or you will be keep on hearing this particular term called as an atom. But what is an atom? What is the size of it? Where is it present? We'll be learning about all this in detail in this grade, especially in your 3rd and your 4th chapter. Right, atoms and molecules and structure of an atom. So in structure of atom, you will be learning everything about the structure. What is it made up of? Okay, so shall we just proceed with the session? Good. So now tell me what are atoms? Where is it present? See, this is a definition for an atom. Just make a note of it. Atoms are the smallest unit of ordinary matter that forms a chemical element. Right? So here you just have to make a note or you just have to look into these two words. Okay, so one second. So what are these two words? One is matter and other is a chemical element. You know what is a matter, right? So matter is nothing but it says about the solid, liquid, gases, and sometimes we'll also talk about plasma here. Correct. So irrespective of their physical state, let it be a solid or a liquid or even a gas, we call that to be a matter, that's all. Right? So all the matter that is around you is made up of atoms. Or we can say when we break them down, we'll end up in atoms. This will be easy. Yes or no? You're just taking this pen, breaking this down. It is made up of plastic that you know. So when we are breaking this down, what will be, where we will result? So somewhere we'll result, right? So that somewhere is called as an atom. And here, see, ordinary matter that forms a chemical element. You know what is an element? Yes or no? So what is an element? For example, we'll talk about sodium chloride. We'll just write NaCl. Okay, so sodium chloride is nothing but the salt that we use. So in this sodium chloride, sodium is a separate element, chlorine is again a separate element. So no, so that is a chemical element. So when we break down the salt, when we observe them in their molecular level, we end up in a chemical element. When we simplify that element more, then we'll end up in an atom. Now is it clear? Good. So anything starts with an atom. And everything, if you break down, will end up in an atom. Clear? Good. So next. Now we'll just think or talk about the size of an atom. Okay, so what is this? It's an anthill. You know very well, right? So when we just look at the structure, the one thing that comes to your mind is ant hill, or ant has built this small ants together, they built their own home. Okay, so in order to reside, in order to live there, as they'll use this as a shelter, they'll use this particular place to raise their babies and to feed their babies. So there where they actually live. Okay, so when we are actually zooming this particular ant hill, what do you see? you will see some very small soil particles, right? So this small soil particles join together to become a hill. Yes or no? See, I'll tell you a very simple relation, okay? For example, in biology, you know very well, when we actually look into our own face or our own self, what you see is a skin. So when we just zoom into the skin, we end up somewhere which we call to be a tissue. Yes or no? So tissues, how do we get tissues? Cells combine together to form tissues. You're clear with this point, right? Just apply the same thing in chemistry. So in chemistry, atoms combine together to form molecules. Let it be oxygen molecule, water molecule, or salt molecule. It can be anything. But atoms have to combine together to form a molecule. So this molecule can be an element, can be a compound, can be a mixture, can be anything. Is that clear? Yes. So whatever it is around you is being made up of small particles. So that small particles is called as an atom. So now we'll just look into the size of an atom. Okay, how big is an atom? All right. So just tell me like what might be the size of an atom? How we will measure it? Measuring the size. How will we measure it? See, for example, if you are going to a tailor to stitch a cloth, so he'll actually use a measuring tape to measure your shoulder size. From here, he'll start, right? So when we are talking about the shoulder size, each one of our shoulder size differs. Mine is L, yours might be S or even XS. I mean like extra small, medium, large. Like that we have different size. Right. So we are using some unit to measure it. Yes or no? So here we'll either use inches or we'll use meters. Yes or no? Centimeter we'll use. Basically, if it is a shorter distance, shorter size, that those things all we'll be measuring like that. Or we'll prefer inches. So in order to measure the size of an atom, there also we are using some sort of unit. Okay. So this unit might be like somewhat new for you, but it's quite easy, okay, once you have that in mind. See, atomic radius is measured in nanometers. See here, this nanometer might be new because so far you are familiar with the centimeter, cm, and meter, kilometer, right? So this is nanometer, nm. Nano means it is so small. All right, smaller, much smaller than a meter. How much smaller than a meter? I'll tell you. See, listen. See, look at this. 1 meter equals 10 to the power 9 nanometer. Such a big number, right? Yes, in order to get 1 meter in terms of nanometer, you just have to have 10 to the power 9. That many zeros. So instead of writing 9 zeros in one line at a stretch, we are just writing the power thing. You know this one, right? In your mathematics, you would have studied. Yes. So next. So now can you just imagine like what might be the size of an atom? It is so small. We cannot even see with our naked eyes. But scientists are using some special equipments to see them, okay? See, listen. And here, this hydrogen atom is much smaller than any other atom. I'll tell you why in the later sessions, but still, just have this in mind. So the size of this hydrogen atom is 10 to the power minus 10 meters. Okay, so normally we have to measure the size of an atom in nanometers, but when we write it, we'll write it in terms of meters for our better understanding. Is that clear? So next, see, look at this. 1 second. Yeah, right. See, this is a hydrogen atom, right? So I told you about the atomic radius. So here, from here, they'll start till here. So this is a radius, right? When you're making it together, it becomes a diameter. So this size is this 10 to the power minus 10 meters. So that is a size of a hydrogen atom. Clear? So next. Water molecule. So what is the formula for water? Oh my God. 1 second. Yeah. So molecule of water, you know very well it is H2O. right? Two molecules of hydrogen combines with one molecule of water to make a water molecule. So the size of the water molecule is 10 to the power minus 9 meters. So this is a normal size of an atom, okay? So it will be like this. So one oxygen is getting combined with two hydrogens here. Okay. So next, see, 10 to the power minus 4 meter grain of a sand, like one sand molecule. Sorry, one sand bit. See from here. So any one of the sand bit which is very, very small. So the average size will be 10 to the power minus 4 meters. Clear? So this is a normal size comparison, like how much small. Now can you just tell me like how much small the size of an atom of hydrogen is when compared to the grain of a sand? Good. So next, see, listen, before we started writing the elements, okay, for example, we were discussing about this water and the molecules of water, right? So there we will be writing water molecule as H2O, where this H represents hydrogen and this O represents oxygen. So no, see, for example, I'll write hydrochloric acid, HCl. This Cl represents chlorine. Or some other terms, hydrochloric acid. Okay, this is hydrochloric acid. So like anything else, just come on, just tell me like something which comes to your mind. Or CO2, that carbon dioxide. Okay, or ammonia, I write NH3. So all these are symbols. Yes or no? We are saying carbon dioxide, carbon dioxide. So here this C represents the carbon. This di represents is being represented by this 2. This oxide is being represented by this O. Carbon dioxide. So when we normally say, we say this to be CO2 or we also say that to be carbon dioxide. So before telling the names exactly, okay, this is the element symbol. Alright, this is a name of the element. Before that, scientists use certain methods or certain symbols to to represent the particular atom. So we'll be discussing about that now. Okay, it is a very simple part in your lesson, but still you have to know this. Okay. So hydrogen, previously it was Dalton. John Dalton is one of the very, very great scientists whose theory of an atom we are still following. Okay, so he came across all this, this elements, and this is a respective symbol that we have to use like that. Okay, so don't get confused with the symbols because nowadays we are using for hydrogen this H only. But this was something which was used in the olden days. Okay, so hydrogen is being represented by that symbol. But exactly what do we write hydrogen as? We write hydrogen as H. See, carbon as C. And oxygen, of course, O. Phosphorus, we write PH, right? Sulfur, S we write. So next, platinum, PT we write. Yes or no? So phosphorus, what do we write? We write PH and then O. Okay, fine. So sulfur we write S and platinum we write PT we write. Yes or no? So yes. So next. But these things, like in the olden days they used. In the olden days, why did they use these symbols? For example, we say, temperatures. We are using this as a symbol, or this is a unit. Or we say it's like alpha, gamma. We write alpha and we write gamma, we write beta. Yes or no? So all these are symbols that we are using, just like that. Okay, so don't get confused with these symbols. Nowadays, we are not using any of this. All right. So iron, we use Fe. So copper, we use Cu. And then silver, Ag, gold, Au we use. Lead, we write plumbum, Pt, Pb. Right. So mercury again, Hg. Right. So these are the symbols that we are using. But these symbols are something which they were using in their olden days. Is that clear? Fine. Good. So next. See, Berzelius is one of the scientists who actually came or put forth the mass of an atom, or he also defined he has written a lot of theories for the atom, whether it might be structure of an atom or mass of an atom or the exact size of an atom. He was actually a chemist, or we can say like he's a scientist who came across, gave us a lots and lots of theories for an atoms. We'll be looking about one such theory, what he has written, okay? So now, see, look at this. These are the name of the elements. This entire column, name of the elements. And this one is a symbol that we are using in nowadays. Okay. And this is a Latin name. So Latin name is like, for example, so these names are completely common. They just pick the first letter of hydrogen. So helium, they pick the first two letters. Carbon, they pick the first letter. Copper, they picked it from the Latin name which is called as cuprum. Okay, so since it is cuprum, we use Cu instead of using Co. We use Co for cobalt. Chlorine, it is same. Cadmium, boron, barium, bromine, bismuth. Sodium, again, sodium, we derived this from the Latin name natrium. Okay, that is why it is Na. Potassium, again, kalium, so that is why it is K. Iron, ferrum, so that is why it is Fe. Aurum, and then what is it? Silver, it is argentum. Okay, here they didn't use Ar because Ar is something which we use it for argon. Clear. So when they are actually formulating the symbols from the Latin name or from their original name, they were very sure that none of the elements should have the same symbol. Okay. For example, yeah. So this is what silver. We are writing it with Ag. Argon. We are writing it with Ar. Right. So this Ar shouldn't disturb, or we are not taking it from this argentum. This is clear? Clear? Good. So next. Nowadays, we are not using or we are not following the methods that the scientists were actually started, like how they exactly started. We are not using them. We are using everything based on this IUPAC, which means the International Union of Pure and Applied Chemistry. So they started giving the symbols for us. Like for hydrogen, it should be H. For oxygen, it should be O. Cobalt, it should be CO, like that. They started giving the elements. And those elements or those symbols only we are using nowadays. Just like SI units in physics. So there are different units, right? So for measuring the distance itself, we used feet, we are using meters, we are using inches. There are a lot of things that we are using, right? But there are certain standard stuff which is called as a SI unit. So those SI units only we are using in nowadays. Similarly, in chemistry also, for these elements, different scientists put forth their own ideas, which we are not following nowadays. We are following only the things that that has been described by this IUPAC. Clear? Good. So now, so according to this IUPAC, as I said before, hydrogen we use H. For aluminium you use Al. And at the same time, we have to be very careful that while we are writing this symbol. See here, when we are writing for hydrogen, it is capital H. So every element, it starts with a capital letter only. So for aluminium, we'll write Al. We don't write Al. Yes or no? For example, this cobalt, here it will be much easy. See, if we write, for example, if we just look at this CO, what comes to your mind? We will not read it as cobalt. What do we read it as? Any guesses before I write? No? Okay, fine. See, we read it to be carbon monoxide. Yes or no? So it is carbon monoxide. Fine. So this cobalt, we have to use it like CO and not CO, which means like we'll just read it to be carbon dioxide or carbon monoxide or something like that. Okay. So now, so when we are just looking at this atom, see, atom is something which is, for example, you know very well, it is something which is present in all matter, irrespective of their physical state. It is made up of everything, or we can say like the matter is made up of atoms only. So when we break down the elements into smaller components, we'll result or we'll end up in one particular thing called as an atom. So this atom has got a lot of subatomic particles, or we can say like it is made up of certain other things also which is present inside an atom. Is that clear? So basically an atom, it is made up of 3 different subatomic particles. Okay, so what are those subatomic particles? When you see here, This center part, you call this to be a nucleus. Okay, so this nucleus is made up of two different subatomic particles. One is proton and other is a neutron. Okay, just have this in mind. Proton and neutron are present inside the nucleus of an atom. And then you have this electrons which is revolving around the nucleus. They are in complete motion. They are continuously moving in their own orbital around the nucleus of a particular atom. And here one goodness is mostly this proton and electron will have equal numbers. In neutron also, in most of the cases, it will have equal numbers of protons and neutrons and electrons in one particular atom. In certain rare cases, the neutron number will be increased or sometimes it will be decreased also. And the electron number is also like that. We can remove and add an electron. Not artificially, sometimes it will happen naturally also. Addition and removal or reduction of an electron can take place. But addition and reduction of a proton cannot take place. If proton is removed from this particular atom, the atom will not remain stable. Is that clear? So you will learn those things in the upcoming slides and upcoming classes. So don't worry, I'm just telling you, okay? So now, we just have to measure the mass of an atom. So how are we going to measure the mass of an atom? I'll tell you. See, listen, in order to measure the mass of a single atom, what they started, it's like they started comparing two or three objects. Okay, so how did they compare? Just look at this circle. Okay, so we know like we have got two different objects with us. So one object, when we look at it, it is bigger. The other object, it is smaller in size. So this bigger object is actually 12 kgs that we know. Because it is big in size, we can touch it, we can see it, we can measure it. Now it is 12 kgs. Now we just have to find the kg or weight of this particular B element or a B object. Okay, so for that, what shall we do? First thing what we'll do is like, we'll try to cut this, okay, into half. Into an exact half, we'll try to cut. Okay. So after cutting, we are now cutting it into smaller. We are just comparing it and seeing both the sizes. Okay, it is not small. It is not equal. So we are cutting it smaller and smaller, and at last we are ending up in 12 pieces. Okay, so this 12 pieces is somewhat okay, like to some extent they might weigh together. We are feeling it like that. Okay. So now what they are doing is like, now we are just weighing one piece of A with the B in a measuring or in a weighing machine. Just like this. Now when we look at this, this particular needle is in its equilibrium position, which means both the objects are having equal amount of mass. Now tell me, what might be the weight of this one piece? Come on. See, initially what did I say? I said this entire circle, like the entire object, it is 12 kgs. Okay, so how many parts did we cut this into? We cut this into 12 parts. So this is one part. So what does this mean? This means that this one part is 1 kg. So what is the weight of this then? We can make this also as 1 kg, right? Because they are weighing together, they are weighing equal, right? So by using this comparison, or we can say like by comparing the weight of 2 and 3 objects, they started finding the mass of an atom. Okay, or this is how they assumed the weight of an atom, and it became true also. Clear? Fine. So mass of object 1 is 1 by 12 that of an object A. We can write it like this also, right? Good. So next. So in order to take a reference atom from all the different elements, so as a reference atom, they started collecting this carbon atom. Why carbon? See, carbon in most of the cases, it will be neutral, which means it will have this electrons, protons and neutrons, right? I'll just tell you. Okay. See, listen. This carbon had equal number of protons, electrons, and neutrons. So this is proton. I'll tell you like why it is plus, why it is no charge, and all those things I'll tell you. But now just have this in mind. So this is an electron. So when we are talking about the numbers of this particular carbon, we got everything to be 6. Is that clear? So number of protons were 6, number of neutrons were 6, number of electrons also were 6. In most of the cases, proton and neutron, like one particular isotope of a carbon is something which is present in abundance. The Cs12 is one such isotope of a carbon which is present in abundance all around the atmosphere. So that is what we are using. I mean, like it is 666, which means like it is a neutral atom, and that is what, like, that is why we are using this carbon atom as a reference atom. Is that clear? Now, so the atomic mass of an atom with respect to one atomic mass unit. Is this clear? So how are we measuring the mass of an atom? We are measuring it with respect to the atomic unit. So this atomic unit, we'll be writing it as AMU. Or simply we'll write U also, but still we will be writing AMU, which means like atomic mass unit. Fine. So now, what is an atomic mass unit? Very simple. Mass unit equals 1/12 of the mass of a carbon atom. The same formula, the A object, B object, how did we compare? The same way only, using carbon atom, we are comparing the weight of other atoms. Alright. So in order to find, or when we are writing it as, solving it as a problem or something like that, then we'll be using this particular concept of 1/12 of mass of a carbon, 12 atom. Is that clear? Fine. Cool, good. So next. So now there is a, for example, I'll just tell you. So this is a human, okay. So this human is 70 kgs. Now we just wanted to find the mass of an atom. How are we going to find the mass of an atom? Very simple. See, listen. This here we are writing this to be 16 atomic mass unit. So this 16 atomic mass unit, or 16, is a number which we already know based on the protons, electrons and neutrons made of the particular protons and neutrons which is exactly present inside an atom. Is that clear? Yes. Good. So now, how are we going to find the mass, or in a particular atom, what gives mass to an atom? Just imagine atom to be an empty basket like this. And this empty basket is having like a very negligible amount of mass. And this empty basket, we are filling it with apples. Okay, so now once we are filling it with apples, and again we are weighing them, what weight will you get? We will get the weight of this apples, yes or no? Because I said like this basket is having a negligible mass. Very small, less mass. So here the weight of this entire object has been given by the apples, right? Similarly, if an atom is there, the weight is given by the subatomic particles, and especially this protons and neutrons. Because this electron will have a negligible amount of weight. Okay, so by counting this proton and neutron, weighing the mass of proton and neutron, we will be getting the atomic mass. Or simply to say, mass number. By counting the number of protons, neutrons, and electrons, we'll get the atomic number. We'll discuss about atomic number a bit late, but just have this concept in mind of the atomic mass. So what is exactly atomic mass? Good. So atomic mass is nothing but the weight of protons and neutrons. Okay. Good. See here. Now I'll tell you how is an atom neutral. Okay. So atom is neutral just because of this protons, electrons and neutrons. So proton, can you see the symbol? It is always positive. So P, you can just have this for plus. Okay, so protons always have a positive symbol, so it is having a plus sign. Is that clear? So electron is direct opposite for them. Electrons are something which is negative charge. So if protons and electrons are equal in number, then the atom becomes neutral in charge. Neutral in charge. So what is this neutron? Neutron doesn't have any charge. They are not positive, they are not negative. So they are neutral. So neutral doesn't mean that they are having some neutral charge on them. It is there to give mass for the particular atom. Okay, so it gives mass to the atom, it gives, or it is responsible for the atomic weight, atomic mass, and atomic number. And here it adds up a good special nature for the particular atom as well. In hydrogen atom alone, the neutrons will not be there in one isotope of hydrogen, because when you're looking at a hydrogen, this is a nucleus. This is an electron. So inside the nucleus, only one proton will be there and only one electron will be revolving around it. Is that clear? That is why the mass of a hydrogen atom is 1. Is that clear? Fine? Good. So now just look at this. This is a chlorine atom. Okay. So this chlorine atom might have 17 protons and 18 neutrons. I said like in some rare cases, this neutrons will have a higher number, right? 17 protons and 18 neutrons. So together, it will become 35 units. In some rare cases, it also can have 17 protons and 20 neutrons. So altogether, it will have 37 units. So how can one single chlorine atom can have different numbers of units? It can have. It is unless and until this proton changes, this is going to be a chlorine atom only. So just look at the number of protons. It is 17 protons. And here again, it is 17 protons. So since only 17 protons are present in both the cases like this is called as a chlorine atom. The numbers or the weight differs because of the neutrons only. And neutrons number can vary. Unless and until the proton number varies, the atom doesn't lose its stability. Is this clear? Fine? Good. So next. Yeah. So yes, guys, we've come to the end of the session. Is the mass number and how the size of an atom clear? Fine? Good. So in our next class, we'll be learning in detail about the atomic masses of an atom. Fine? So yes. So until and unless I meet you in my next session, this is Lavanya Ilangovan signing off from e-learning. Bye-bye. Take care.